Hello everyone, my name is Joseph Birch and I am a research associate at Michigan State University in Dr. Jessica Meisel's Fire and Ecosystem Ecology Lab. Today I'll be telling you about the relative contributions and drivers of fire energy across 16 years of wildfire data in California mixed conifer forests. After a century of fire suppression, a combination of changing climate and altered forest structure is resulting in a shift in fire regimes towards large, high-severity fires across much of California mixed conifer forests. These forests represent an important and diverse ecosystem type that spans from south central California to the northern portion of the state. As climates continue to change and fire regimes shift, we can expect that these systems will experience fire regimes that are notably different from pre-European colonization. Additionally, these fires will coincide with increasing drought and beetle epidemics, setting the stage for dramatic forest change. Additionally, as these forests die, there is a potential for positive feedback with climate change as carbon is released from these forests, resulting in altered ecosystem functions and disrupted forest resilience. To help mitigate these unwanted forest changes, we need to better understand how forest characteristics alter fire behavior and ultimately influence wildfire effects. Ultimately, we need to understand how fire behavior results in immediate post-fire change. Because of the difficulty in assessing immediate pre- and post-wildfire conditions, many studies have focused on changes reflected several weeks or months post-fire. Now, while extremely useful, these observations do not capture the immediate changes from wildfire and how fire behavior influences forests. Variations in fire behavior can lead to dramatically different fire effects, which can have long-term consequences for forest recovery and ecosystem function. Gaining a better understanding of the drivers of fire energy and the immediate changes after wildfire can help us predict impacts on forests and design better management strategies. To help fill this knowledge gap of identifying the drivers of fire behavior and immediate post-fire change, the USDA Fire Behavior Assessment Team, or FBAT, has established pre- and post-fire measurements of mixed conifer forests across the last 18 years. The measurements they take include measurements on the structure, composition, and biomass of the overstory, understory, surface, and ground fuels. Immediately after the plots burn, the FBAT team revisits the plots and assesses the plots for change. The FBAT team also collects information on fire behavior, including the rate of spread, flame lengths, and other measurements. Collectively, this dataset provides a globally unique dataset to explore how pre-fire characteristics drive fuel consumption and fire behavior. If anyone is interested, full methods on the FBAT measurement scheme are provided on their website in the lower left corner. We used 16 years of FBAT data and sought to identify the answers to several research questions. The first were if there were differences in the immediate pre-fire characteristics of the forest and whether the characteristics differed significantly by fire severity. We were also interested in the immediate post-fire changes by strata across different fire severities. And finally, we were interested in what was driving fire energy and whether those drivers differed with fire severity. We were interested in fire energy because it is closely related to fire line intensity, and it is a rough surrogate of all consumed fuels in a fire. The FBAT data was collected across 112 forest plots in California, seen here on the right in green circles. And at each plot, there were variable radius tree measurements taken for a pole-sized plot and an overstory tree-sized plot. Additionally, each plot had between 1 to 3 Brown's transects and vegetation transects oriented around each of these fuels transects. Collectively, these characterized the pre- and post-fire conditions. Additional measurements were set up to capture various estimates of fire behavior as the plots burned. We took the measurements of each fuel strata within the forest and calculated biomass using standard biomass equations. We then used remotely sensed derived metrics of fire severity, the differenced normalized burn ratio and the relative differenced normalized burn ratio, as well as categorical fire severities from the MTVS website. When you look at how the distribution of plots fall across these categorical fire severities, you can see that most of our data ranges from unchanged to moderate severity, with only 13 plots within high severity. Our plots ranged in age from burning in 2005 to as most recently as 2020. For calculating fire energy, we use the low heat of combustion, which is 18,600 kilojoules per kilogram, adjusted by minus 24 kilojoules per kilogram per percent of fuel moisture within each category of consumed fuels. Finally, we used a multi-model inference approach to identify pre-fire drivers of fire energy using a combination of topography, weather, and pre-fire fuel values. This approach moves away from standard p-values and calculates all possible a priori combinations of variables and assesses these models by AICC. Models with lower AICC are considered better, and the very best models are averaged together for a global model. Within the global model, each variable is ranked by relative variable importance, or RVI, which is a measure of how influential the variable is in influencing the dependent variable, which in this case is fire energy. Moving on now to our results. In this panel, you can see the biomass of the various strata broken apart, where we have pre-fire characteristics, post-fire biomass, and the change from fire. While on the x-axis, we have all plots lumped together: unchanged severity, low severity, moderate severity, and high severity. Starting first with total biomass of all strata combined, we can see that unchanged and low severity plots had the highest pre-fire biomass, but that there wasn't very much significant difference between these categories. For the post-fire change, there was no significant differences with categorical fire severity, despite a trend of higher severities having greater absolute biomass loss. When we look at the tree strata, we see a much stronger trend of unchanged and low severities having greater above-ground tree biomass before and after fire, though high severity did have greater loss of tree biomass than did the lower severities. When we looked at downed wood, which encompasses 1 through 1,000 hour fuels, there were no significant differences between the pre-fire, post-fire, or change from fire biomass of these strata, though once again there is a trend of higher severities having greater absolute biomass loss as well as pre-fire biomass. For the forest floor, which encompasses litter and duff combined, we have the same non-significant result, but the trend remains where higher severities have greater pre-fire biomass and greater absolute loss, though once again this is not significant. However, when we look at the proportional loss of biomass by strata, we do find some significant differences. For 1,000-hour fuels, there were no significant differences, though you can clearly see that the higher severities had greater proportional loss of 1,000-hour fuels. We do have some significant differences in the proportional change of biomass for 100-hour fuels, 10-hour fuels, and 1-hour fuels, where high severity fires had significant differences relative to low and unchanged categories. Meanwhile, moderate severities is non-significantly different from both the severities that are higher and lower. When we look at the forest floor, duff had no significant differences across categories, while litter we did see that higher severity plots had greater proportional loss of litter relative to low severities. And finally, when we look at surface fuels, seedlings, shrubs, grass, and herbs, we see a similar trend of some categories having no significant difference, with high error in some of these lower severities. But we did find that in grass, there were significant differences between the low category and the unchanged category. Moving now to the proportional contribution of each strata to fire energy, we can see that fire energy in general increased with increasing severities, though this was not statistically significant given the range of error in some of these categories. When we look at how each strata, the consumption of each strata, contributed to fire energy, you can see that by far the forest floor is contributing disproportionately to the fire energy. Subsequent to that, we have the shrub and seedling and downed wood, which altogether make up the vast majority of the biomass being consumed. There are no clear patterns and no significant difference across categorical fire severity, once again highlighting that these remotely sensed fire severity classification systems do not capture well the variation within some of these plots. When we used a multi-model inference to identify the pre-fire drivers of fire energy, which is somewhat a proxy for consumption, we found that several key variables were highly important in determining how much fire energy was produced. Principally, we had 1,000-hour biomass. This is pre-fire 1,000-hour fuels. The duff biomass, the litter biomass, the shrub biomass, and the standing snag biomass, though this was not a significant portion of the fuels that were consumed. Finally, the relative humidity of the air was the only non-biomass variable that was identified as having a high RVI. Generally, variables with an RVI over 0.5 are considered highly influential on the dependent variable. So interestingly, this implies that fire energy is largely a product of pre-fire biomass fuel loadings within these plots, and that fire weather, represented in our model by mid-flame wind speed, relative humidity, and fuel moistures, is of lesser importance in determining the absolute amount of consumption across these plots. Notably, our data set is biased towards lower severity plots simply because the FBAT team is under restrictions in their ability to go out and measure wildfires under extreme fire weather conditions. So understandably, this data set is largely skewed towards those plots where fire weather is not likely to be a driving dominant factor in determining fire behavior. However, it's interesting to note that duff and 1,000-hour biomass, largely considered smoldering fuels, are as important as they are in determining fire energy and represent a pool of biomass that disproportionately contributes to the consumption within the forest. Finally, to revisit our research questions. For our first question, we found that there were few significant differences in pre-fire biomass by strata. Notable differences included lower severity plots having greater above-ground tree biomass than did high severity plots. Despite a lack of significance, we did see consistent trends of increasing downed woody debris and forest floor biomass with higher fire severity. One reason for the lack of significance may be from high variation in severity within each 30-meter remotely sensed pixel. Other studies, such as Furness et al. 2020, have found that remotely sensed metrics of fire severity can fail to capture variation in fire effects within each pixel. For our second question, we found, again, a lack of significance when comparing absolute biomass change across categories. However, relative change across some strata was significantly different, with higher severities generally having greater relative change in fuel biomass. Finally, we found that pre-fire ground fuels, 1,000-hour fuels, and standing dead biomass were the best predictors of fire energy, and that the absolute consumption of these strata did not vary with greater fire severity. So some of the takeaways here is that there's a lot of variation in these pre-fire conditions, and that there were no significant differences in pre-fire biomass for most strata, despite there being a trend of higher severities having slightly higher pre-fire forest floor and downed woody debris biomass. Could be that with larger sample size of higher severities, we may have been able to detect a significant difference across these categorizations. And finally, we found that fire energy in unchanged low and moderate fire severities is largely driven by ground fuels. Before I finish up, I just wanted to mention some of the future directions and current work with the FBAT dataset. There's continued establishment of new FBAT plots in California and across the country to help expand this dataset with new measurements of carbon stocks and below-ground forest health and better refinement of fire behavior variables. And in 2021, we were able to go back out and remeasure most of the FBAT plots to assess forest recovery. And hopefully we'll be sharing those results in the coming years. Finally, I would just like to acknowledge all of our funding partners and everyone who has helped collect and manage this data across these last 16 years. And I thank you all for your attention. If you have any questions, please feel free to contact me at the email below. Thank you.